numbers, right? So it should not be dependent on just one set or one combination of numbers, right? So creating multiple samples. Now remember what we have done here. We have 9 images. From one image, we created 9 images, right? From this 9 image, we can create 4 more. So that's already 36 images. So from one sample, we have created 36 samples, synthetic examples. Again, having just black and white, changing the color of the image so that it doesn't really depend on the color features which are present. And then something called random crops. Random crops are basically, as you can see here, just cut out different parts of the image and use each one as a training example. Now, 36 times 4 is another, like we already have 36 numbers. And if I am going to apply all of these color changes to each of this, then that is again another whole set of synthetic samples. There's something called fractional pooling. Fractional pooling, I think of it as making the image more pixelated. So basically, we have an image, and all the pixels within the red region will be compressed as one color, as one number. Like take the average over this small region, over the red region, average over the green, average over the red, and replace all the pixels with the average value. Now, what did we achieve through that? A very pixelated image. So we are basically creating a low resolution image by maintaining the size, by maintaining the 24 by 24 arrangement. Right? Did you get that? Usually for reducing the image resolution, we reduce the size, right? But for training, we only get, yeah, thanks. For training, we need to feed all the images to be of the same size. So fractional pooling helps us achieve that. So it maintains the image size, but makes it more pixelated. And then what are called cutouts. Now, conceptually, cutout is very similar to your dropout actually. Why? Because in both, we are addressing the same issue. We are making sure that the network training doesn't really depend on a few particularly important features. Right? So this is the image version of dropout. So if we try to implement dropout at the image level, that's what was cutout. Or implementing cutout at the within the neural net architecture is kind of your dropout, right? And then combining images is very interesting. So here what happens is we combine the features of dog and cat within the image. Now, if you see here, we can see the cat. We can also see the dog part, right? So the same image has both the labels. It has cat and it also has dog. So when it is being trained for cat, it will have a different error detection criteria. When the same image gets labeled as category 2, it will have a different error detection criteria, right? So it just makes the network more efficient by making the task really difficult. Okay. So all this people did, and ultimately they were able to come up with a very nice architecture. They were able to add more layers, and ultimately AlexNet really won the competition, right? So until 2011, it was only um, so until 2011, people use traditional approaches, SVMs, and all the traditional methods of computer vision. If you look at some of the terms and some of the things that people try to do, it would be really, I don't know if it's the correct word to use, but cute. Uh, Today, like there was literally an algorithm which will find corners, which will see how two lines meet and a corner is formed, right? So for that algorithm really improved the performance of the network of the classification by another 2%. And people were really happy with this. And then came AlexNet with the picture with all these innovations, and you can see there was almost a 11% drop in performance. So the innovation was GPU training. It had only 8 layers and around 60 million parameters. Any questions in AlexNet?
When you say drop in performance or drop
Oh,
in
error. Sorry, drop in error. Error. Sorry,
yeah, yeah. Thanks.
drop in error. Yes, sorry.
Yes.
Yeah, Professor, could you elaborate after the 5% human error, the next three
Yeah,
models, 2015, 2016, 2017? Thank you.
I'll come to that. Yes. Okay. Anything about the AlexNet till now? Okay. So if AlexNet is clear, I think we are good with any scanons. And that's when people realize that, okay, let's just add more layers, right? So by the next year, or the real innovation was actually changing the 11 by 11 filter to, I think, 7 by 7 filter. In the initial first layer, how Alex had used 11 by 11, right? So ZepNet in 2013 just used a 7 by 7 filter, and again the performance improved, right? So why didn't Alexa use it? Probably their setup, their architecture, the constraints did not allow the use of a 7 by 7 filter, right? So 11 by 11 was how much they were able to do within the deadline of the competition. So they had one full year to come up with better resources, better ways of handling the bigger data. So ZepNet, just small filters, nothing else. It is exactly AlexNet with smaller filter. Okay. And then people thought, okay, let us just add more layers. That's all. Right. So suddenly from 8 layers in 2014, people went to 16 layers, 19 layers. That's where the VGGNet came into the picture. I know it's somebody else's talk, so I don't want to spend a lot of time here. I'm sure they will explain it. But people just added more layers, that's all. Okay. And that is the start of this idea called, okay, let's just dump more layers, more parameters, bigger models, mammoth models, better training. That's all. Right. So the idea that if we have a lot of data, the way to handle this huge amount of data is to build a mammoth neural network architecture, right? That is coming from here basically. When people progressively saw that if I add more neurons, smaller filters, deeper layers, I'm getting consistently better performance, right? So BGGNet had there's a reason why it is 16 to 19, and I'm sure that the group will explain it. Um, for the first step, people said, okay, we go deeper, we get better, right? So that is 6.7% is the error rate. The same year, GoogleNet came up with its own, Google came up with its own architecture. So it had something called Inception module. It is a 22 layer architecture. Again, if I have time on the last day, I'll explain what this Inception module is. These are legacy architectures, so there are better ways to handle things today. ResNet is a much more popular architecture, okay, which you see in 2015. And see how the jump is from 8 layers. We went to around 20 layers in 2014 and straight away to 152 layers. That's the depth of that's how deep the ResNet architecture is, right? So 152 layers, accordingly, so many neurons, that much processing, that much acceleration. And they implemented what's called skip connection. Is anybody doing ResNet in this group in the for a group presentation? Is anyone doing ResNet?
No, Prof, we chose Claude Instant 1.2.
Class itself.
Instant. Yeah, instant.
Okay, so you didn't choose ResNet. Okay,
Yeah.
okay, sure. Jansi Rani says no processor. What does that mean? I didn't get that.
I think she meant no professor because we're all in the same group. So you asked if
Okay,
we
no
do it.
professor.
So she
Okay,
must,
okay.
yeah. So she must have been saying no prof, but by mistake.
As a typo, yeah, I get it. No processor. Just when we are talking about GPU processing, somebody says no processor, and I thought, okay, that's not consistent. Okay. Right. Okay. So the 5% human is actually the human error rate. So if I'm going to show 1000, if I'm going to ask if you show an image and ask them to classify an image into 1,000 category, into one of a thousand categories, humans are wrong 5% of the time. So 5% is the human error rate, right? So by 2015, we had a network which actually surpassed human performance. Okay, so when the image competition started, the goal was to come up with a system which will at least mimic the human performance. And so within a couple of years, we came up with architectures which could actually bypass human performance, the human error rate of 5%, right? That's what the 5% there is. And then it got progressively smaller, 3.6, and then Google then came up with another version, V4. And 27 was the last time this competition was held. And then they actually announced that, there's no point in having the competition anymore because we are, 2% is what? That's okay. So anything that's better than 2%, it's just an add-on. So we have already achieved what we wanted. So the competition just ended. But the legacy continued. We just learned something really important that if we add more connections and if we are able to optimize the performance of the network for a deep architecture with a lot of parameters, we can actually do a very good job in building a very efficient, or at least one of the metrics, accuracy, we can improve it. We can reduce the error rate. That's what people learned. And that laid the foundation for all the further architectures, right? And this logically, it led to your transformers with of course more innovation in the way that we are when we see RNNs next tomorrow, RNNs and LSTMs, we will see how the ideas borrowed from the GPU acceleration, all these ideas which we have here, how they just got reinvented and a variant of this got implemented somewhere. And really, it exploded into the transformer stage that ChatGPT brought up. Any questions, please? Here?
Prof, I didn't get the part. How did we land up to the transformer? What was the main breakthrough?
So the major breakthrough was if we add more layers and have more filters or more parameters, more weights. Basically, more weights and more layers leads to better performance. That's the consistent story here. Okay, which was kind of obvious before that, but they didn't have the infra to implement it. So the infra, engineering, architecture, everything came together to really test the hypothesis that if we add more weights and build a deeper neural network, we will actually get better performance. Any questions?
Yeah, Professor.
Hmm.
For AlexNet success, why did the researchers not add more layers? Also, no. Why did they add more layers instead of making each layer wider?
Like in 2012 itself, you mean? Do you mean in 2012 itself, why didn't they just add more layers, right?
They added more layers. Why don't they make the layers wider?
Like wider as in add more
Um,
neurons, add more filters. Like instead of 96, have like
yeah.
500 filters.
Oh,
Again,
yeah.
constraint, infra constraints. From
Ah,
2012 to 2015, 2016, that was actually the age when the GPUs, TPUs, Google came up with its own tensor processing unit, and then there is graphic processing unit. So the infrastructure optimization that took a couple of years.
I see. Thank you.
Okay. So what I have here is basically the AlexNet architecture. So there's an input, and we are removing the thing with Zoom is there is this one which I have to manually hide. One more. Now, the input images, as I mentioned, 224, 224, right? And did we calculate the number of input parameters last week, like manually for how it works in CNNs, how it works in ANNs? I think in the lab we did a version of that, right?
Yes, yes.
Okay, great. So here, this number makes sense. The 3 by 3, 64. So we have 64 filters.
So here the color layers are being fused in the first layer itself, right?
No, so there's into 3 is there, right? So it is 3 channels.
Okay, okay. And that keeps continuing till the end. Okay, till the FC layers.
So only here there is, so this 3 comes from this 3,
Okay,
right? And the 64 is the number of filters.
okay. And beyond that, it's a fused image.
So this 64 gets carried over here, and this 64 is the number of filters in this layer.
mm.
This 64 gets carried over here. 128 is the number of filters in this layer. That's how we read it.
Yeah, what I'm asking is, Professor, 224 by 224 is the pixel and 3 is the color layers, right?
Correct. RGB. Yeah.
Yeah, now my question is the color getting fused after second?
No. No. So what happens is, so we have a color. We have this R and then G and then B, right? So and we have a 3 by 3 filter. Okay. So the 3 by 3 filter acts on this separately, acts on this separately, acts on this separately. So at the end of it, if I have one 3 by 3 filter, I have 3 feature maps
And that goes
per
to
image, per image.
and that keeps continuing till the last convolution layer.
Oh, yeah, that's why if that's what you mean, yes, correct.
Yeah, okay, got it.
There is no fusing happening anywhere.
But in the FC, it will be fusing, right? Because
It
FC
will be
doesn't.
flattened. It will be flattened. So there's no fusing per se. So what happens is
Hmm.
if there are like 14 pixels here or no 16 pixels,
Hmm.
1, 2, 3, 4, 5, 6, 7, 8 like that up until 16. What happens in FC is it gets flattened like this.
So we are flattening. What will
Yeah.
happen is the 2.3 million.
Hmm.
So post
Where is the 2.3 million coming? Here. Okay.
So after the 2.3 million, the other colors 2.3 million will come. So that way, the color to color information exchange will be lost out, right?
Okay. Color to color. Even here, we are not. Okay. So the color to color information, it's lost here itself because each feature map is an independent thing.
Yeah. We are dealing. I mean, it was never
These are never part of the
utilized.
game.
It was never
Here is the
leveraged, and
here is the first time it is being leveraged
at the last flattening layer.
at the flattening layer because there's a neuron sitting here
Hmm.
which is getting this input and which is also getting this input.
And what is surprising me is that at the flattening, they are not being interleaved. Instead, they are being stacked or serialized. Is that correct?
It's flat, yeah. So at this point, if you remember the 788, 784, 28 by 28, how we made like a real, like a straight line of the image, that's how
Hmm.
it is.
Yeah.
So the R comes, and then the G comes, and then the B comes. Like
Okay, it is.
if
You will
you
say it is
fix up,
interleaved.
like remember, okay, there is no RGB here. In the A and N, it was R, G, and B. But
Hmm.
here, up to 16, okay, up to 16, it is feature map 1. And then from
Okay,
17 to
got it,
32, it is
got
feature
it,
map 2.
got it, got it, got it, got it. Understood. So how they do feature one from R, feature one from G, feature one from B, and then the next feature, or
The
they.
RGB is lost here.
Hmm.
See, yeah, at this point in the CNN,
Hmm.
by the time it comes to the fully connected layer,
Hmm.
any RGB information is long gone.
Okay, got it, folks. Thank you.
In the RGB, it might not really know that it's RGB, but as you can see here, if we keep going back and see where a particular pixel came from, it will obviously map to the R layer in the first layer. If we go, this is very traceable, right?
Hmm.
Because we are specifically creating these things
Hmm.
from the input. If we use a 3 by 3 filter, it will
Hmm.
go to this part of the first convolution. And if that is preserved in the first pooling layer, it will be this pixel. And then from there, it goes to the next convolution, it will be this pixel. So we can trace back and we
Hmm.
can say that it is actually coming from the R layer. In that sense, yeah, the RGB information is kind of there. But what I'm trying to say is the fully connected doesn't really care if it is, RGB or HSL or whatever.
Hmm.
As far as it is concerned, it is a pixel, it is a number. It just
Hmm.
sees how this number is related to the 10th number or the 100th number or 4000th number. That's all.
Hmm. Thanks, folks.
Okay.
So just to understand that, Professor, so if the image quality is a very high quality image,
Mm.
that means that would add more constraints to the network. Is that a correct inference?
High quality image would add more constraint in terms of making it difficult to process.
Process, yes.
Computationally, yes, computationally it's going to be more difficult.
Okay, okay, so like if that is the case, then because slowly the world is moving towards more high quality images. So does that mean that all these things will become obsolete and they cannot work anymore? Or we need
Okay.
something different?
Okay. So um, These are legacy systems. You have to remember that, right? I'm talking about the constraints in 2012. Constraints in 2012 are not the constraints in 2026. So we can deal with high resolution image with a CNN probability.
Okay. Okay. Yeah, got it. Yeah, thank you.
Okay, so the reason I have this slide is if you see the blue numbers are slowly increasing from the first image to the last for first layer to the last layer, but the red numbers are actually decreasing from the first layer to the last layer. So the red numbers are basically the size of my feature map. So I'm having an input image that is 224 by 3. That is around 150K pixels to deal with. Okay, 150K to 8-bit numbers to deal with. Now that produces a feature map which is of this size. Okay. Con3 is basically a 3 by 3 convolution, let us say. Okay. And that has 3.2 million numbers. And if I keep adding that up until here, per image for one forward pass, I have 24 million pixel values to deal with. And if each one has around 4 bytes of worth of information, that is around 96 MB for one image for one forward pass for training these images. Did that make sense? The 24 million here, that comes from adding all these numbers 150 to 3.2, 1.6, 800, all this if I could add, that comes to ballpark of 24 million. Okay, and with this number, for every image, we need a space of 96 MB per image per forward pass. Okay, like this, we are doing how many, like thousands of images, but at the same time, if we do like a single image training, then the number is 96 image. Remember, single image training never works almost always. We always use a batch size of 128, right? So 128 times 96 MB is the amount of information that needs to sit in my processor while training the image for one forward pass. But it has to remember the weights. Remember, so it can't just be this, and then it has to back propagate, it has to weight update, back propagate, calculate error, and all that. So the resource requirement is immense. I'm showing this calculation to show you where the necessity for GPU comes. Right? And then, as a result of this, we have extracted, these are basically the weights. Okay, so a 3 by 3 filter, 3 layers, and 64 filters gives me 1728 weights to train. Like this, in each layer, I have weights to train, and as I go deeper and deeper into my architecture, I have more and more weights to train basically. Okay, so by the time I come to the last fully connected layer, I have around 40 million weights to train, and even a simple AlexNet is a 138 million parameters, 138 million uh, weight architecture. Let that sink in. This is in 2012, right?
And to think that how much how many parameters does human brain has? That would be really.
Okay. Yeah. Yeah. Correct. So we are trying to mimic a human system which has probably maybe like millions of more neurons actually. Right? So it is really impressive that in 2012, the people they built an architecture which handled these numbers, these kind of numbers. Okay, let's keep that aside and see go into the CNN and see what the CNN learns. I think there's a repetition slide. We have already discussed this. In the initial layers, we have very generalizable features like lines, corners, edges, and those they really combine to form slightly more complex shapes, and those complex shapes they combine to form much more complex features, right? And the trainable classifier just sees how two wheels are arranged to make a bicycle or to make a car or to make a lorry. Okay, at the start, all the low level features they are just getting seeing these corners, these edges. Some color information is there. Okay, and the next mid-level features, they see how two lines they combine to form a edge like this. Okay, or how two lines they combine to form a circle. So we have a circle now, right? And the high-level features, they basically see how two how two circles they combine to form uh, either a car or how the two circles combine to form a bicycle, right? That's what the high level features they really learn. And that's the job of the trainable classifier, which basically sees how all these high level features they work with each other. Now, if we move the argument a little bit away from there and see what defines an object, go to a little bit of philosophy and see what differentiates a face from a truck, from a chair to an animal, to a door or whatever. If you look at what's happening in the neural network, some of these low level features, that is, the ability to detect edges, like to find that there is some luminance difference between this black area and this white area, this black area and this area, between this eye area and the forehead area. Okay, those things are common, which is very much the same as finding the difference between this part of the car to this part of the car, or this part of the elephant to this part of the elephant, or this part of the chair to this part of the chair. The ability to detect the edges is common between all these images. Okay, and if you go to the mid-level features, a chair has these four legs, these horizontal geometric shapes, whereas a car also it has some commonality with the chair, like there are horizontal lines, there are vertical lines, there are diagonal lines, right? Whereas it's very different from what a face is. A face has more curves, more features like this, right? What I'm trying to say here is, yes, lot of the low level features are common between these four categories of images. A lot of mid level features are actually common if the the end images are similar to each other. Like for car and chair, some of these features are could be actually common, right? For elephant and tiger, or for elephant and let us say a hippo, some of the or some other animal like cat or whatever. Cat is funny. Um, which animal is not flying? Okay, rhinoceros probably. Okay, so there some of the mid-level features are common, right? The real differentiation between objects happens only in some of the higher levels as to how the two circles are combined to form maybe a bicycle or maybe a two-wheeler or a car or a truck, right? So some of these lower level features are common, but remember at the same time, some of these lower level features are very hard to extract, right? Because you see how the memory requirement progressively comes down, right? So some of the earlier layers, they require actually a lot of memory space during training. And those are the features that can be shared, right? So if I want to do a cat versus a dog classification or a table versus chair classifications, well, some of the edge detectors are common. Edge detectors are basically detecting the edge, not in these higher levels, but in these earlier levels, right? So people thought, okay, the earlier level features are hard to extract in the sense they are very resource demanding, but at the same time, they are the ones that are shared. It is also generalizable. An edge detector is an edge detector for table versus chair classification or cat versus dog classification. Okay, that's the idea behind transfer limit. So people thought, why not train like a huge data set and then reuse some of the earlier layers, like here. Okay, so the assumption here is if I want to do a cat versus dog or a table versus chair, at least some of these features are going to be common. Why? Because there are going to be edge detectors, there are going to be corner detectors, there are going to be all sorts of very generalizable features. As we get more and more data specific, that's when extracting the data specific features are is also going to get difficult. So people thought, if I want to do a table versus chair classification, but I already have a model which is trained on cat versus dog, I will just borrow the first maybe 5 layers. Why? Because the first 5 layers are the most demanding layers as well. That's where there is a lot of memory requirement, right? And a lot of low level features are extracted. Did you get that point? That is the basis behind our transfer learning. Did that make sense? Am I on mute?
Yeah, I can hear you.
Yeah. Did everyone get the idea of transfer learning? The logic behind it.
Professor, just one thing. What I understand that it's like we have a kind of some stages here. It's like the first stage is like we are dealing with the in the low level features with the high resolution images or objects, and in the high level let's say features we are dealing with the kind of low level or low resolution images. Is that right? Did I understand it right?
So it's not low resolution images. The image is the same, but here we are progressively extracting more and more feature maps. By definition, feature maps get smaller and smaller as you go deeper into an architecture.
This is because we have at the beginning we have enough of image, let's say data, so we go low when we go more advanced or the to the other level. Is it like that?
So if you look at the basic, let's say architecture here,
Mhm.
what I have here is a 224 image, right?
Okay.
But I use 11 by 11 filter and the feature map reduces to 55 by 55.
Okay.
So the size progressively reduces. By the time I am in my 1, 2, 3, 4 or fifth conversion layer, my feature map is just 13 by 13. We started with a 24 image. We ended up with 13 by 13. But now why did this happen?
Uh-huh.
Because I have my input image and then I'm doing a convolution, right?
Okay.
Remember how we did convolution? By nature, convolution reduces the size of the output,
Yeah.
right? On top of that, we are doing stride. We are using bigger filter depending on the filter and all that, right? So that is the goal of convolution, to get the feature instead of raw pixels, to reduce the given area into some meaningful representation rather than the raw representation. So as we go deeper into a neural network, the number of the image, the size of my input progressively reduces. This is the feature map. Only in the first layer, it is actually the image size. As you go deeper, this is actually the feature map. All these are feature maps. So the feature map gets the most important parts from my input image.
Okay.
Okay, and that is why it is very demanding, because my initial layers usually have bigger feature maps and bigger images, as you can see here. I'm dealing with a 24 by 24 image, and here I'm dealing with a 13 by 13, which is very handleable. If I can use the words, that's the word,
Okay.
right?
Yeah.
So that's what people are leveraging in transfer learning. So people are saying the initial layers are hard to extract, okay, difficult to extract and train, but those are the layers that are generalizable. Okay, generalizable. Okay, so the earlier layers are generalizable because they just detect edges and corners and all that, which is anyway common between any image, any image category. But those are the parts of the neural network that is also difficult to train, because it involves more parameters, because it involves bigger feature maps and bigger input size, right? That's why people use transfer learning. So the idea of transfer learning is I have a whole image that is tested on all these different kinds of filters. But what I want to do is I want to do a cat, or maybe a um maybe a cat versus dog classification. Okay, I know that all these images were trained in the ImageNet data. Now, the ImageNet data is this mammoth data which has all different types of category of images. It has from bottles to it has beads to animals to it has, huge image set. So if I want to do a cat versus dog, I'm pretty sure that some of these features are actually a part of my whole training. So what I would do is I will just reuse, I'll knock off the fully connected layer, which does a 1,000 class classification, which is too much for me. And I will replace that with an FC2, two class classification, cat or dog. That's all. Instead of training my own full data set. Why? Because it's a waste of my resource. I know that some of these features are not really um, uh, worth training from the scratch. Now remember, one thing I didn't say, this cat versus dog, this data set is coming from probably my device, my personal phone. Okay, so these exact cats and dogs, this whole training network, it has not seen. What it has seen though is cats and dogs from different parts of the world, right? I will take the initial layer from there, replace the last layer with my own fully connected layer with two categories, cats and dog, and I will just train it for a couple of iterations, right? So I'm replacing only the last fully connected layer, customizing it for my data set. Now, what if I have a slightly bigger data set? Here I'm assuming that I have only a couple of examples of cats and dogs. Okay, let us say I have like 200 images of cats and 250 images of dogs, right? I'm counting on the existing cat and dog feature within this whole data set in order to give a good performance in the top layer. Now, if I have a slightly bigger data set, if I have like 2,000 cat images, 2,000 dog images, what I would do instead is, instead of just replacing my final layer, I will unfreeze more layers. Now, what I'm telling this neural network here is, I have my own data set. Okay. And I know that you already have cat and dog features within your training, right? I am interested in only the two categories, cats and dogs. I am not worried about chairs or tables or whatever. Okay. So I will make the network more efficient by unfreezing more layers. So until the pooling layer, I will borrow all my weights. But when it comes to the fully connected layer, I'll probably change this to instead of four, because I'm only doing a two class classification, right? So I will probably change this to my own architecture, like 200 neurons or whatever. And I will do a two class classification. This will be a FC200 or whatever. Why am I doing this? Because I have a lot of samples. I know, let us say I get 5,000. Because I have a lot of samples. And my data set is very similar to the existing data set. Where I know that some of these features are already present here. I'm only topping it up with more data, which is customized for my requirement. Right? Now, what if I want to instead of a cat versus dog, I have a different problem. I want to do an good leaf versus dead leaf classification. Okay, I will go back and I will erase all the inks here. So previously we had a cat versus dog. That was my scenario 1. What I did was I only changed my last layer. Okay. Here again, my scenario 2, cat versus dog, but my data set is big. I have lot of images, 5,000 images in each category. Okay. So what I did, I trained more layers. Okay. Now let us look at scenario 3, where I am doing a good leaf versus a dead leaf. Classification. And again, I have lots of examples because dead leaf, good leaves are easy to correct, right? I just need a camera and I just need to go into the field and just take pictures. So I'll get a lot of images. Let us say I have 5,000 in each category or 10,000 even. Okay, but the problem here is not the number of samples, but the image, the feature extraction that is going to have. If I want to train a network from the start, this is probably not enough because these train on millions of images. I have only around 10,000 images per category, right? It is still not enough to train from scratch, but it is enough to show enough samples. So what I would do here in this scenario is, anyway, my low level features are transferable, generalizable. So I have dead leaf, bad leaf, or cat or dog. Edge detection is going to remain the same, right? So I will freeze all these. I will okay. So again, I would fourth scenario, large and very different. So I have a large uh, corpus, but it is very different from the pre-training that this data set is used to. This data set, the pre-training has not seen good leaf or dead leaf, but it has seen thousands of general image features. So instead of training just my classifier layer, I would unfreeze more layers, probably until probably here. Okay, I would retain the low level features and the mid level features, and I would train from here. Now, what is the advantage? Low level and mid level features, they are still very resource demanding. They are still very resource demanding until here, right? So I would still get the weights of all these parameters with lesser memory consumption, because the majority of memory consumption is done in my previous layer and I'm actually borrowing it, right? So what I would get is, using low memory, I will train more parameters, which is specific to my data set, my good leaf or dead leaf data set. So I would train more layers. Now, this works in a number of examples. The use case will be good leaf, bad leaf. A lot of industrial use cases is damaged product or good product. It can be disease. It can be like a skin, normal skin versus a skin with some lesion. It can be retina, normal retina versus abnormal retina. All these use the transfer learning concept. They borrow in all of the earlier, the weights from the earlier layers and just train the top few layers. For this, train smaller waves. That is the whole idea behind transfer learning. Now, the fourth scenario that I did not really talk about, and it is very difficult also, is when your data set is small and it is also very different from your training data set. And classic example for this would be a very rare skin condition or a very rare disease, a very rare anomaly, right? Where the disease prevalence itself is less. So the number of images that you have for that data will be even lesser. Like let us say there are only 200 images or 150 images from your hospital data set for a particular disease, right? And it is also very different from general features like cats and dogs and chairs and tables. So training that network will be very difficult. So that's where you try a lot of things. You use transfer learning, but you unfreeze more layers. You probably try to train a CNN from scratch, or you go with a completely different approach. Any questions still here? That logically brings us to the end of CNNs. So scenario 4 here will be a rare disease, uh, less samples. Less samples, and that will be right. Different tips. Any questions still here?
Will there be a higher chance of overfitting if you unfreeze more layers with a
Yeah,
small data set?
yeah. So both the risk of underfitting and overfitting is actually existing in transfer learning, right? Because if we try to rely too much on the pre-trained data set, the features in the pre-trained data set, then obviously in the training data set look different, it will look good, but when the real world data comes, the features could be so widely different that it might not actually work. So overfitting is an issue. Underfitting is also an issue if the specific examples that we actually took in our training data set, if it is not truly representative of what's going to come in real world data.
Thanks.
Okay. So object detection, I think I'll give an intro before we go for a break. So I'll stick to my promise of all problems in machine learning are either classification problem or regression problem. Object detection is a classic example where it's going to be both. Every image, I mean, firstly, we need a box around an object of interest. We saw how this is a regression problem when I talked about this during our introduction sessions. Um, we'll talk about that again. But basically, we need to find the coordinates of the starting point of this box, ending point of the box. The four corners of the box basically become a regression problem, right? If my image is, this is my 0, comma 0, and then I have row, comma, column. So this is my 0, comma 1000, and this is my 1000 column. 1000th row, first column, yeah. And then I have 1000, comma 1000, right? So how is it a regression problem? It basically needs to find if the coordinate of this within 1000 to 1000 range, what is the number that would be given here? Again, from 1000 to 1000 range, what is the number that's going to come here? Solving that is basically a regression problem, right? It is very similar to finding your salary. If I want to find the exact salary of a person, and if I build a regression model for that, it predicts a number on a continuous scale. Very similar here. There's a continuous scale from 0 to 1000, and it predicts a number. And if, for example, it predicts a number like 24.78, just round it off to 25 or 24. That's all. Right? That becomes the regression problem. The classification problem is basically within that box, what is the classification that is there? Till now, we have seen CNNs are good at classification, right? So we just need to give a label to the thing in the box, and that is basically a classification issue. So in classification, we had one image and one main object within that image, and we just classified that as, we gave a label to that image. So that's all. That is classification. In object detection, we have two things going on. We need a bounding box and a label for that bounding box. So the label for this bounding box is human. For this is dog. Okay. So in image classification, I have one image in, one label out. In object detection, I have one image in, multiple coordinates of the bounding box with the corresponding label for each of the bounding box. So depending on what I'm going to train my data on, here I have two bounding boxes. One box is here, one box is here, and one label for that. Now, you might ask why it is not detecting TV, why it is not putting a box around this and saying TV, or putting a box around this and saying cabinet. That is doable, depends on what we want our object detection algorithm to do, right? For the same thing, you can actually, if you want to find an action detector, okay, if you want to do action detection, the same label instead of person, it will be stooping or bending. Okay, and for the dog, it will be sitting instead of dog, right? So the label is very, very task dependent, very, very case dependent. What I want to achieve through that neural network is what the label is going to represent. Is that clear? Any questions?
So there are multiple problems here, right? One is about the size of the bounding box, and then what is within that bounding box, and then the position of the bounding box, right?
The size and the position are interrelated. You see,
Okay.
if it gets the coordinates, the XY coordinates,
Hmm.
then that becomes easy. So there are multiple ways to do this, right? So if I have a starting XY position, and
Okay.
if I can come up with a width number and a height number,
Hmm.
obviously then this number is inferred from that.
Okay. I need four coordinates. It can be a x, y, LH or x1, y1, x2, y2,
Ah,
right?
yes.
And
Yeah.
those four, and that will define the rectangle. And then what is the, I mean, if it is going to be just detecting a known object, then it is very simple. It stops there. But if it is going to be a multi-object classification, then it has to also encode what is the object detector, right?
Ah, correct. Yeah.
And
So yeah, so this is classic detection versus labeling issue. So if you just want to, like, if it has only like if you have your camera,
hmm,
it puts a box around your face, but it
hmm,
doesn't put a label called face because it
hmm.
does only one job. Its one job is to detect face.
And the confidence metric of the object being there is a performance metric, right?
Ah, correct. Yeah.
Okay. And regression, you are saying the uh, confidence of regression comes where, Professor?
The regression basically comes it is with the coordinate, finding the coordinate. No, the x comma y coordinate. How does it find it?
Okay, okay. Ultimately, like we connect it to the metric, right?
Yeah, correct. So it instead of predicting the salary on a continuous scale, it
Hmm.
predicts the starting position of the bounding box on a continuous scale of 1 to 1,000.
Yeah, here I have one challenge, Professor.
Mm.
In any of the classification problem, for example, like when we use a neural network classification, the
Mm.
threshold gets determined by the system as a tunable parameter, right? So it tries to optimize itself so that the threshold is variable. Is it correct?
What threshold are we talking about here?
The classification threshold.
You mean when you do the logistic regression, the
Like
threshold that you
I
decide?
have a logistic regression, and let us say that like I have two classes.
Okay, okay,
Or
okay,
if I am
yeah.
having a
Now,
multi-class also, then
okay, yeah, correct. Okay, what's your question? With the threshold,
now,
what do you do? Mm.
so, though my there my if I am taking my ROC AUC or
Mm.
any such metric which are basically analog,
Mm.
and I am tuning my threshold to mm, maximize the, let's say, the ROC AUC.
Mm.
In that case, I do not call that as a regression. I still call it as a classification. Is it correct?
Ah, correct, correct, correct. That is, I mean, if you say, if you think about it, then everything is a regression problem then. The moment you introduce threshold, only it becomes a classification problem.
Okay, okay, okay. So in that sense, understood. Yeah,
Yes.
but
Yeah, this kind of thinking is very important when you are solving classical machine learning algorithms. I don't know if I told this in this session or some other to some other group. I came into like I've been doing image processing for quite some time actually, doing some segmentation work, image transformation work and all that. But to get into proper machine learning world, it was only in 20, I would say 19 or so, when people were actually moving towards LLMs and neural networks. So I used to interact with all these people who are very hands-on, who have been building logistic regression, linear regression for like 15 years now. So that was the time when if you knew random forest, you are an ML expert actually. So and when a business use case comes to them, the first thing that they would think of is, okay, so it is a, I mean, when they think about it aloud, they would say, okay, so it's a classification problem. Okay, so it's a regression problem. The first thing that they say out aloud after they understand the problem statement is, what kind of problem is it? So even the token completion which you are doing now in LLMs is a massive classification problem, right? Instead of predicting what is the cat or dog, you just have 1,000 or 10,000 birds, and you are saying the maximum probability is this bird. So it is a multi-class classification problem, right? It is almost like if you give a problem to somebody with a doctorate, the first thing that they think is they form the hypothesis in their head. They form the null hypothesis. And I'm not joking it. I'm not kidding it, right? So if you go to seasoned researchers, statisticians, people who have been publishing papers, some sort of a hypothesis statements comes to their mind the moment you give a problem to them, right? So that is a kind of mental exercise which, if you are in the field, if you are in ML, if you are in AI, you really need to, it helps you simplify the problem and bring the problem into your fortress. That is your strong point, and from there you can actually take it further, right? I don't know why I digress, but that was a good story. Anyway, I hope I answered your question, right?
Yes, thank you.
Okay. Okay, I'll just start with the classical approach here. So, how did people start, do object detection before? They will just start with a random box within an image, and these dimensions of this would again be like the flip of a coin. They start with some random number and do what is called a sliding window. So you slide that over an image until you are happy that you have detected some sort of an object within it. Okay. Now every time it slides over the image for every position, you actually do an image classifier. You do a dog, not dog classification, right? That's how complicated object detection was. I hope you can appreciate the complexity. First, we need to come up with the correct size. For every size, we need to kind of do an image classifier at every point, using SVM and all the traditional ML that we actually did, right? Detect edges, build a model, do a dog versus not dog classification. Okay, and then the next stage was doing something called an image pyramid. Now the problem with the sliding window is something that works for one size of the image might not actually work for another size of the image, right? So one sliding window will work in one uh, um, in one dimension, where one dimension of the image, whereas if you increase or decrease the size of the image, it might not work out. So people said, okay, let's combine that with something called an image pyramid, and just make sure that it works on every scale. Okay, so upsample or downsample, and preserve the scale of the sliding window. Okay, that's how traditional object detection work. So ultimately, we hope that we come up with the correct size that will bind the object within the box. Come up with the correct binding box. Okay. I'm not going to talk about this, but again, the problem here with this is something that works on one scale in one rotation. Even if you rotate the image a little bit, the algorithm would fail. Very fragile, very brittle kind of an algorithm. Okay, that's when CNNs came into the picture, and people actually started using CNNs for object detection, which we will see after the break. Let's take a 7-minute break and come back. All good? Time for a break?
Yeah, okay. Thank you.
Let's continue. So one of the earliest object detection mechanisms, which algorithms, which actually moved from traditional ways to detect objects, like a combination of the sliding window versus the image pyramid, was the RCNN. So by this time, actually, the ImageNet had introduced CNNs and they were successful. AlexNet was introduced. So people were like, let's stick to what we were doing here using the sliding window. But instead of every segment passing through a image classifier, which was anyway not very accurate, let's pass each of the window through and CNN. That was the idea behind RCNN. R here stands for regions, regions with CNN features. Okay, so this kind of builds on how perception happens, again, from psychology, neuroscience inspiration. So people kind of try to say that a big object is actually a combination of smaller features, right? So there is the handle, and then there is the cup, and the mouth of the cup, and the bottom of the cup. All these, they combine to give the perception of a cup, basically, or a coffee mug. So people went reverse and they thought, okay, let the algorithm recognize regions which have the potential to have features, right? So we start with an input image, and we just make 1,000 different cuts in the image. We crop the image like 2,000 smaller subregions. Each of the region is going to go through a CNN. Okay. And within each of this, there's going to be a classifier. If we are interested in three types of categories within the object detection, each region will be classified as airplane or person or TV monitor. Right? Pretty simple. What is the problem with this? What we are doing here is take an input image. We just make 2,000 random cuts, not, we extract 2,000 regions from the image, which has the potential to have some CNN features, right? And send each of this into a CNN network, like an AlexNet or VGG or whatever. And each region will give a classification. What is the problem with this?
Is it we are going to waste a lot of computation power for meaningless classification or something?
Yeah, correct. So we have per image, we are doing 2,000 image classification, or at least if it detected some plain regions where there are no CNN features, and if you go to ignore that, even like hundreds of classification per image, right? So that is very computationally inefficient, right? All the 2,000 regions, remember, they go through a region with CNN features classifier. So if there are features within a region, then that goes to the next level classifier and an object is detected. Okay. So this takes a huge amount of time because it needs to classify 2,000 regions per image. One of the reasons we want object detection is that it has to happen at least real time or near real time. What I mean by near real time is, let's take a picture of picture of a, what to say, of a plant, and we want to find the region where a leaf is dead. Okay, or picture of a skin and put a box around the lesion, right? Or an industrial line where there is a crack. It has to not only detect the crack, it has to put a box around the crack, right? Now, all of these, it require at least some real-time implementation, right? When the product is in the line, the crack should be detected. Running this takes around 50 seconds per image, right? That is not very efficient. So RCNNs, obviously, they have a huge problem. You know, and then people moved to something called fast RCNN. So they said, okay, instead of all the 2000 CNNs, instead of doing 2000 classifications, let's take an image, do one CNN, get the feature map, simultaneously we will run the image through something called an object proposal region, but we will not use CNN for this. We will see if that area is plain or if it has some features. We will use something called a similarity search in order to find object proposal region. So instead of blindly sending 2000 regions through your CNN and doing 2000 classifications, people decided I'll take an image, I'll pass it through CNN once, I will store the feature map. Parallelly, I will use another algorithm called similarity search to find parts of the image where there are features likely present, right? And then in the next stage, I will map this object proposal region with the feature map. Now remember, the feature map is a very traceable thing, right? So I can actually backtrace and I can say the fifth pixel in my layer 10 is mapped to pixel 1 to 10 in my input image. That's doable, right? That's very much doable because we really control how the CNN happens. We might not know what is exactly there, but we might actually know where a given pixel was in the original image. I hope you can understand. This is an important concept. So you backtrack that using the region of interest and you compare the proposed region with the feature map in order to identify. That is your fast RCNN. So the fast RCNN is going to give two things. First, it's going to give a softmax probability estimate for the K object classes. Okay. So if I want to, if I'm implementing an algorithm to find cats, dogs, humans, horses, okay, I have four classes. So it will do a classification. It will give that output. It will also give me four numbers which serve as the bounding box positions for each of these object class. How did it do the classification? Remember, it did a similarity search and it found regions in the image which look interesting, like something is going on there. And then it passes those regions through a classification. And then it takes help from the feature map and it sees how the feature map, like what does this particular feature map contain within this K classes? Does the feature map represent this interesting region or this interesting region or this interesting region? So it compares the interesting region that was proposed using similarity search with the corresponding feature map which came from the CNN. Now the feature map also has information about where a particular pixel is related to my input image because it's traceable. So that also gives us a bounding box proposal. So it gives the bounding box, gets the bounding box approximate ballpark figure from the feature map, and then does a regression on top of it to arrive at the exact bounding box. Right? Uses the feature map data to compare it with the proposed region from my similarity search algorithm in order to find if the feature map represents, this object or this object or this object. So at the same time, it is doing two things. It is giving me class output. It is also giving me bounding box position.
So can you
Does
go
that
over
make
that
sense?
once more? Can you go over that once more, slightly slower, please, if that's okay?
Yeah, sure.
Maybe just step by step, once again, if that's okay. Thanks.
Yeah. This is why let's do it. I will just take a couple of minutes, some time to explain the similarity search. Okay, so this is the similarity search algorithm. As you can see here, similarity search is basically is scanning the entire image for places where there is some likelihood of features being present. So if you take sky, for example, this is a vast area of nothing big happening. So it compares, randomly picks a point and then compares the next pixel to it in every direction. And then it says, okay, nothing is happening for 2 pixels away, until 10 pixels away, until 20 pixels away. And then it says, okay, in this whole region, nothing is happening. Simultaneously, it is also picking another point in the image, and it is basically saying, okay, now I'm detecting something. There is something going on here in this border. So it does a bit of what is called segmentation, and based on that, it says something is going on within this box. Okay, like this, it kind of sends all these boxes called these object proposal regions into the network, into the algorithm. Simultaneously, what's happening is simultaneously, the network has also done a CNN. It has sent the whole image into CNN just once, and it has stored feature maps. So we have feature maps, low level, high level features. Now the feature map actually, remember, the feature map actually has global information about the image, right? So the feature map at some point will say that some horse-like figure is going on in this part of the image, right? That is sitting somewhere in the 15th, 20th layer in the 20th activation map. There is an object proposal which is coming simultaneously from the similar research algorithm. These two are combined, right? The object proposal says something is going on in this region because it comes with the coordinates, right? that is compared with the feature map, and then it says, okay, let's go to the feature map to that particular location and see what's going on there, right? And then a classification is happening as to is it a horse or a dog or a cat or a human? Because only one thing is going on there, right? So it can't go wrong there. The similarity search basically says something is going on in this region. The feature map would look something like this for the whole image. It would look something like this, right? So this comes with XY location. That XY location is compared with the feature map, and then it says, hey, you know, you say that something is going on there. I am also detecting something there. So let's send this region to the classifier. Now the classifier does a 4-class classification. A horse or a cat or a dog or a human. That is the first output that comes out of this network, the softmax output. Okay. Remember, the similarity search also is coming in with some coordinates, some xy, and the feature map also has some xy here going on. The feature map can actually trace it back to my input image and say, okay, I'm coding the 7th row, 10th pixel from my input image in this part of the feature map, right? So now I know a ballpark for the bounding box. From there, it solves a regression problem and it fine tunes that bounding box basically. So maybe the proposal region, it did not give this exact box. It gave something like this, right? Now the job of the bounding box regressor is to make this box into this box. That is the second output that comes out. So we have a region of interest from the feature map. This is the ROI. Because remember, inside a feature map, all these areas are going to be black. If something is going on, there you will find some white, some shade like thing going on. So the feature map says this is my ROI. The similarity search algorithm says something is going on in this part of the image. Both of these are combined to give two outputs, a softmax and a regressor. Did that make sense? Does that make sense? Okay, thanks. All right. Okay, so fast RCNN really made things better. Really made things better. So the training time, leave the SPPNet, I'm not talking about that. The training time really got from 84 hours to you were able to train the network in 8.75 hours, right? But more importantly, during inference time, the fast RCNN was very fast. Okay. One of the things that people actually noticed was if we are going to test an algorithm, or if you divide the time between the time it takes to do the region proposal and to make the classification, you will notice that consistently there is a delay. There's a 2-second delay in just finding the region of interest proposal. So the algorithm spends more time doing the similarity search and proposing the region of interest than actually doing the bounding box and the classification, which is the core of object detection, right? So people started working on how can we make the region proposal better, because we can live with the zero point 0.3 second. No, that is that's almost real time. That's as good as it can get. But people try to minimize the 2.3 here. The 2.3 is the time that is spent on um, um, proposing the region of interest, saying that within this huge 500 by 500 image, this 10 by 10 is my region of interest. Just to say that it is taking a lot of time, right? That's where people thought, okay, let's make that better. And they said, instead of using a similarity search algorithm, I will let the neural network itself propose the region of interest. Okay, so in faster RCNN, you see how much time they have spent in naming these algorithms: RCNN, fast RCNN, and faster RCNN. Um, it is like the fourth born in the family, right? So you name the first with all your heart. By the time you are in the fourth child, you just call him X or Y. So that's the faster RCN network, where there's an image, convolution layers are there, feature map is there. Until this, it is very similar. But here it takes a slight detour and it says if the feature map is black, like nothing is going on there, if there is some lighting up going on in the feature map, then some features are actually present. Now, just with this information, it is able to do a image classification. So now the proposal is not coming from an external algorithm. It is coming from the feature map itself. Okay, CNN happens, the features are extracted, and then it traces back and says, this area in the feature map is coming from this particular area in my image. And each of this goes through a classifier basically. Rest all is very similar to your fast RCNN, except the only difference is instead of implementing a similarity search to propose regions of interest, then the region of interest is coming from within the CNN training itself. Is one of the feature maps itself becomes the region of interest. Now that greatly reduced the inference time. So it took around 0.2 seconds to do an inference, which is really like very, very fast. So faster RCNN is almost real time. It is actually still used in a lot of algorithms where time is not a big issue. In the sense, let's take two scenarios, two use cases. One use case where um, something where a human should be detected. One of the let's say theft, for example. Okay, a jewelry store is there. Somebody walks in with into the jewelry store with a mask and some weapons. Right now, detecting the mask is in real time, very fast, is extremely important. Because if there is a camera that is located strategically, it can actually shut the door and it can lock before the person reaches the second door, door number 2, right? So that is extremely real time, very real time thing happening. Imagine a second scenario where a medical professional is taking a picture of an X-ray or something, and the X-ray puts a small box around a lesion and says, "Okay, here is where the lesion is." Which of these two would require very high latency? Which of these two would require high latency, but not too very high latency? Which of these two scenarios would require higher latency? Or in other words, lesser inference time?
The first
Situation.
scenario is more urgent.
The first scenario is obviously more
More
urgent, right? Yeah,
Yes.
exactly. So that's more urgent. You want it to happen in real time. The door, I mean, it's not really detection. It should detect, and then it has to take further steps on that. It should send a signal to the automatic door to kind of lock it, right? So every second, probably every microsecond matters. Now, even a 0.2 latencies that would actually be too much in scenario 1 for the theft scenario. But for the medical professional who is taking a picture and who is actually seeing that X-ray on the screen, they can live with a 2-second delay or a 0.2-second delay, right? Yeah, I'm not sure if I'm allowed to say that they can wait 2 seconds for the little box to appear on the screen. Maybe the even 2 seconds is too much when you scale it to across 200 patients per day in a busy OPD and all that. Um, but the second scenario, faster RCNN is definitely enough for the medical image, right? Uh, you take a picture and 0.2 seconds or 0.3 seconds later, a little box appears around the lesion. Whereas in the first scenario, even a 0.2, 0.3 second would be too much because a lot of other steps need to cascade based on this first detection. That's where people thought, should we really stick to these RCNN based approaches to object detection? Here I have two scenarios. First is faster CNN. Next is faster RCNN. As you can see here, it has obviously missed a few objects like umbrella and all that. So one of the things with faster inference is reduced accuracy. Sometimes the accuracy will be lost if you if you try to optimize the time. Okay, the time and accuracy are always um, related. They always fight with each other to make our life difficult. Right? So that was faster RCNN. And that's when people thought, okay, look at how we are solving an object detection problem. Why did people start with the sliding window approach initially? That's because they knew only to do classification problem. Right? They felt that we can solve a detection problem using my classification approach, using the approaches that I have for classification. That's why I started with a sliding window because I was better at doing a cat versus dog versus horse classification. And what I did, I broke the image into smaller regions. And I said, see if there's a cat here, see if there's a cat here. That was my idea behind sliding window, which later evolved into the RCNN, which again, so I just came up with sophisticated ways to create that initial box of saying, okay, here is probably where my object is. That is almost um, um, like the story which goes, Like the student who prepared an essay on a cow. So he knew everything about the cow. The student knew that the cow has two horns, four legs, it gives milk and all that. But in the exam, the question was about tree. Write an essay on tree, on the uses of tree. So this guy just he only knows what essay on the cow. So he wrote everything he knew about the cow, and he finally said, "This cow was tied to a tree." Right? So it's almost like that. Like we know only to do classification. So I'm force fitting a detection problem in a classification box. That's obviously going to cause trouble. That's when people decided, okay, let us look at a object detection problem as an object detection problem. Let's not do the two-stage approach. Let us not do object proposal region and then sending each of this region into a CNN. So however fast, however how much ever improvement I bring to the algorithm, it is still bound by this two-stage approach. Right? That's when people said, let's take a different approach and come up with what are called one-stage detectors. So one-stage detectors, basically, they predict bounding box over an image without the region proposal step. As a result, they are generally faster. Okay. As a result, they can actually good at recognizing irregularly shaped object also. Right. And that was the YOLO algorithm. So YOLO basically stands for you look only once. You only look once. Sir. You only look once. Okay. So that was my YOLO, which basically said this is going to be a single stage detector. We are not going to do the two stage thing. So it takes in an image and breaks the image into grids. Okay, it does a 7 by 7, 5 by 5, 11 by 11, whatever. Breaks it into smaller grids, and for each grid, it comes up with this kind of a vector. The first number in the vector says if there is an object within that grid or not. Okay. The second number within the grid basically gives some coordinate for the bounding object. So if there is no object, remember all these numbers, they turn 0 automatically. Why? Because there is no object detected. So for for an image which is largely blank like this, we have already ignored all these regions, these corner pixels, right? Because we know nothing is happening there. So that would give us a score of 0, and all these numbers would again scale down to 0. If there is an object within that particular box, within that particular grid, it gives the coordinates of that object. Like within this grid, it says, okay, this is the bounding box for object. If there are multiple objects, it just gives the vector just becomes longer. That's it. Okay, but it has only half of the object here. So this bounding box gives only like part of the story. And this gives the xy coordinate, the height and the width. So xy, height and the width of the object. Finally, it gives like a class code. If you want to do like a 1000 class classification, this will be a 1000 vector. Basically a softmax. Okay. So that is basically my YOLO. So my YOLO is able to look at the image as a whole. Ah. So my YOLO is able to actually look at my image as a whole, and it gives a class probability for every grid, and it also tells me what is the bounding box within that grid, right? So if the first bounding box, if this bounding box says that, or if this grid says that there is a bounding box here, that information is combined with this grid with its own bounding box information, right? So those two bounding boxes are combined to give a bigger box to basically complete the box. Okay, so all the orange has detected a bicycle. All the pink has detected a background, or all the orange, I'm not sure. Orange is probably the background. All the blues are the grids which have detected a dog, right? So it has basically been able to put a box around the dog like this, and a box around the bicycle like this, because the bicycle kind of starts here and ends here. It takes the bounding box that is suggested by this grid, right? Combines with the bounding box that is suggested by this grid, and says that the coordinates of the final grid is this command. Starts here, ends here. Okay, and each also has a class probability map. So, and all these things are happening simultaneously. Right? That is exactly how the YOLO network works. Lot of variations of this YOLO has come. YOLO, you can say, is kind of the state of the art in object detection. Okay. I think in some of the lab, we will discuss some case scenarios and see how we can solve a given problem. But essentially, that's what your YOLO is. Instead of doing a two-stage approach, it does a one-stage approach. It looks at the image in its entirety. Okay. The grid is a hyperparameter. You can do 7 by 7, 11 by 11, 5 by 5, whatever. For each of the grid, it says is there an object or not. That automatically excludes no huge vast areas of my image. Imagine this is doing a medical image detection or a lesion detection, and my whole image is like this, and this is my leaf, and here is my lesion. Here is where something is going on with the leaf, and somebody is implementing an CV system in their huge hectares of data to find if a leaf is infected, and so that all the crops it doesn't spread. That is a business problem I want to solve, right? Now, what YOLO does basically is, if you integrate a camera into your tractor or in your drone or somewhere, the drone just needs to fly once and it will automatically detect this. And when it does that, YOLO, the class for all these other grids, right, they automatically become zero. You see how much we have saved in the region proposal alone. That is the real power of YOLO. Did you get that? Now the downside is, if it is too small, YOLO might not be able to detect it. At least the initial YOLOs, but later on, people optimized it, and yellow is fairly accurate now, actually. This is the kind of algorithm which will detect the theft, which will sound an alarm and shut down the door immediately, because the detection is actually happening in real time. The theft detection is especially a very interesting scenario, because there are only so many ways in which a robber is going to come into the jewelry store explicitly, right? Like a weapon detection, or a mask detection, helmet detection, or something where your face is covered. If it detects that the face is covered, it will just raise an alarm. That's all. Right? So these things work very efficiently in real time. Any questions till here? So the algorithms which we saw here, the faster RCNNs and the YOLO, is kind of the state of the art in object detection, even nowadays. A lot of the architectures that we saw in CNN, the foundation was laid by Alex, right? That's why I spent a lot of time in that. But the ResNet, the VGGNet are still very good at doing a classification problem. Okay, the same this thing example that I can take, to use a VLM, to use an LLM for image classification is very accurate, but it also involves token cost and API calls and all that. Whereas a CNN is very, very easy to implement. Okay, so if you have enough data and if you can train it well and you don't require um, anything fancy, you just want a CV system which will do a label, which will give a label to an image. CNNs are surprisingly still very common for that particular use case. Okay, and your euros and object detection algorithms are still very popular even in the age of LLMs. So we didn't just study what to say legacy systems just to see how these things evolve into LLMs. They are actually used, like a lot of the business case that we discussed today, use cases. A number of use cases, people still use CNNs and object detection algorithms. Any questions?
So one question.
Yeah.
So here you go first.
Thanks. One question, sir, just to, you've been walking us through the various different use cases as well, for each architecture as well. But I'm just trying to think of, now you said that we constantly compare that now the LLMs are around, and that kind of becomes like a moment in time benchmark of where, we are right now. If you look at the simplest, like, consumer intervention that's in all our hands today, which is just our cell phones with, where you can just upload an image onto Google itself, and Google is able to tell you what's in the image, and, irrespective and it dives deep, etc. What do they use in this technology that's in our hands on in our mobile phones every day?
So the mobile is basically edge deployment. So we need something that takes up less resources, but is also faster. So usually there are networks there's something called mobile net, which is optimized for mobile deployment actually. Like how we saw ResNet and Google Net, VGG net, there's something called mobile net,
Right.
which works great in mobile devices, right? So if you integrate that into any of your existing object detection algorithms, so usually it's not one thing, it's a combination of different algorithms.
Got it. And they are also able to then index it or query it with their Google image search results as well to kind of find some relevance and identify what it is and go into the source of where this can be procured
The,
hypothetically.
so the things like Google, we don't know what's happening, but that's very much possible. They very likely use they have their own labs and their own implementation. Um, the real implementation for this comes for the end user, right? Not end user who wants to implement something simple in their workforce of maybe 200 employees. company, right? Some surveillance system, something that where they can actually build this. If you have enough resources, you can build anything. It is only
Right.
resource constraint things that the real engineering, real architecture design comes into the play. That's when a good knowledge of all these architectures, when to use what, and all this comes into the picture, and you can come up with your own stuff.
Got it. I guess like in today's day and age, like even Amazon allows you to click a picture and upload a picture and it identifies the closest object they have available on the platform for sale.
Yeah. Yeah, probably, yeah. So how that would work? So it's probably getting the image that you upload to train its data better. That's one thing.
Got
The
it.
second thing is probably it implements two detection. So in the image that you upload, there will be some object detection algorithm which will classify an object into one of the n classes in its database. Um, and it will find that well, that's basically it, right?
Got it. Got it.
It looks like it's comparing two things, but it's not actually. If in the
Hmm.
back end, if it is actually doing an n class, where n is the number of items in their database, it is actually doing only one task. It's not even comparing it with something internally, in an image internally.
Right. Right. Got it. Thank you.
So, yeah, Sam.
Yeah, Professor, I can see the urgency of, for example, during an assassination attempt, where we
Mm,
really need to identify the object, you know,
mm,
in the picture. The
mm.
other application is self-driving cars.
Correct,
Self-driving
exactly.
car.
Yeah.
If you can just speak very briefly, what's the state of the art
Yeah.
self-driving
So
cars?
So YOLOs became the object detection algorithm in automatic driving couple of years back. Okay. Whatever said and done, VLMs, LLMs, the inference time is not even comparable to what YOLOs can actually offer. Okay. Um, so a typical algorithm would look like the road is not supposed to have humans by design, right? The role of a self-driving car I mean, right. So a road should not have humans by design. So when it detects a human, but not in the side path, but in the area which it has marked as the road, if there's a human, it will apply a brake,
Yes,
right? Or human
yes.
or cat or whatever. Anything apart from car and bike, if there's anything else within the road in front of it, it is going to apply the brake. It's as simple as that.
So YOLO is being applied on self-driving cars today.
Likely, at least couple of years back, but I can't think of some version of YOLO, not the YOLO actually. YOLO has gone through a lot of evolution, but some version of YOLO is still within real-time detection.
Right.
Self-driving car, especially, I would say very highly likely, but I might have to come back to that.
Thank you.
Okay, so I think we are at 9:15 and I don't have a lot of slides for GANs really. So tomorrow, first thing we'll finish GANs. And anyway, it's going to be done in detail by one of the groups. So I know the slides are a lot, but I promise I'll keep it short. Okay. So tomorrow, let's start with GANs and then let's go on to RNNs. Again, I don't have a lot of slides for that. I can even share it with you if you want. Okay. Okay. Here. So this is basically what I have for my RNN and LSTM lecture. Okay. So as you can see, only 30 something slides, 37 slides. Um, so we'll be able to do this fairly. And the human in the loop is again a very small topic, I guess. So I guess that's all we have. Let me just double check with the materials.
Sir, could you please update today's slide because I may need to have a revision before joining tomorrow's class.
Yeah, sure, yeah. Oh, okay. So let me quickly share my screen to show where we are. Okay. So this is us. Okay, so RNN and LSTM. This we will do, so GANs and this we will combine tomorrow. There's only one topic, reinforcement learning essentials, but that is not a 3-hour topic really. So we can combine that with the lab session on, tomorrow is the lab session. Okay, what I'm going to do is tomorrow I'll convert it into a theory session because some of these reinforcement learning concepts is actually required for your presentation. So I would feel comfortable if I complete this before before the presentation, right? So next Saturday we will move the lab. I hope that's okay. So lab 3 will be here and tomorrow will be um, a combination of GANs and RNN LSTMs. Because it's really important to understand RNN LSTM and how it evolved to whatever transformers we have today.
So, Professor, tomorrow you will be starting from the RL backgrounds and
Yes. So
and
tomorrow the first half an hour I'll do GANs, and then the next probably 2 hours I will do RNNs, and then last half an hour if I have time still left I will do the reinforcement learning.
Okay, and you will be reaching up to DRLs.
Yes.
Fine.
So, and I'll move lab 3 to next Saturday.
Okay.
Okay. And usually I don't keep my lab sessions as, let's study this in theory, like how we had our lab session, right? We learned a lot of new things in the lab also. It was not like we did this in theory and then let's do this in lab. So I actually reserve a few concepts that we can actually do in lab, like the parameter calculation and all that. So I'll probably combine a few concepts that I have in theory along with the lab and we'll do that.
Thanks, Professor. In fact, it was very good actually. The last lab, we learned a lot.
And thank you. Okay. I think that brings us to the end of today's session. Let's meet.
Actually, Professor, can I ask a question about this individual part of the assignment?
Sure.
So I believe that you said that talk about a limitation or whatever for one of the LLM that you're covering. Does it have to be technical? Could it be operational or governance perspective or business perspective?
Anything.
Okay, thanks.
All right, guys. Thank you. Have a good rest of the day. We'll meet tomorrow.
Thank you.
Thank you.
Bye.
Thank you, Professor.
Bye.
Bye-bye.
Thank you. Thank you, Professor.
Thank you. Yeah, thank you, Professor. Bye bye.
Thank you.